In the last session, we have learned if we successfully transform the matrix, we could solve the differential equations. So in this session, we are going to study such a transformation of a matrix. If a linear transformation of a vector satisfies the following equations, A is a matrix and X is a vectors, the product of the AX is equal to the lambda X. So in this situation, X is called the eigenvectors of matrix A, and lambda is a corresponding eigenvalues. Let's see the situation. If we consider the this kind of matrix, and X vectors, then if you calculate this matrix is becoming 2 times 1 once, then this is actually is X and satisfy the equation, and then this 2 is a lambda. Okay, so eigenvector is a 1 1, eigenvalue is a 2 in this situation. Also, if you consider this is A, this is X, if you calculate product of the AX, it becomes 3 times 2 ones vectors. This is X. So eigenvector is 2 ones. And this is lambda. Is the eigenvalue is 3. Okay, so in this situation we could confirm eigenvector and the eigenvalues. Then we'd like to combine these two equations into the single equation. So assume that A has 2 eigenvalues of the lambda sub 1 and lambda sub 2, and the corresponding eigenvector is x sub 1 and x sub 2. So this means we have these two equations. So these equations, A x1, A x2 vectors is combined to form the single matrix. Is expressed lambda x sub 1, lambda sub 2, x sub 2. And the left hand side can express A x sub 1, x sub 2. This becomes a matrix. And the right hand side, so if you consider the x sub 1, the x 1 1, x 1 2, and x sub 2, x sub 2 ones, x sub 2 twos. So this becomes, using the component, lambda sub 1, x sub 1 1, lambda sub 1, x sub 1 2, lambda sub 2, x 2 ones, lambda sub 2, x sub 2 2. Okay, then this equation actually is going to be expressed the product of the two matrices, x sub 1 1, x sub 1 2, x sub 2 1s, x sub 2 2, and the lambda sub 1 0 0, lambda sub 2. Then this part is becomes x sub 1, x sub 2, lambda sub 1 0 0, lambda sub 2. So we have these equations. This is A x sub 1, x sub 2 can be expressed. So this is exactly same with this equation, second lines. And if we multiply in the both sides of the inverse of this matrix, then inverse of the matrix. So if you multiply inverse x sub 1, x sub 2 inverse A x sub 1, x sub 2 equal x sub 1, x sub 2 inverse x sub 1, x sub 2, lambda sub 1 0 0, lambda sub 2. So this becomes a unit matrix. So this becomes 1 0 0 1. So it becomes lambda sub 1 0 0 lambda sub 2. Okay, so we have these equations. By multiplying the inverse of the matrix of the x sub 1, x sub 2, we have this equation. So we obtain the diagonal matrix if we know the eigenvectors and the eigenvalues. Diagonal matrix has a component eigenvalues. The equations we solve is given by these equations. And we like to transform the equation using these eigenvectors, the inverse of the y. So find the derivative of the both sides. So y dot equal x sub 1 and x sub 2 is a constant. This is a constant matrix. So x dot. This is exactly equal to this one. The derivative for the x dot, you can substitute these equations here. So it becomes ax from this equation. If you multiply the x sub 1, x sub 2, y equal x sub 1, x sub 2, x sub 1, x sub 2 inverse x. So this is a unit matrix, becomes x. Then you can substitute. This is here. Then it becomes this one. And then as we studied, this part is expressed with these equations. So we'd like to substitute this into the here equal y dot. Then once we have these equations, as I explained, y sub 1 and the y sub 2 is gonna be expressed with this equation. Two equations becomes independent with each other. We could solve the differential equations independently for the y sub 1 and the y sub 2. Once we discover the solution for the y, you can substitute this y to find out x. The solution x is expressed by the sum of the exponential lambda sub 1t and exponential lambda sub 2t. Okay, and the lambda sub 1 and the lambda sub 2 is the eigenvalues. So then you might understand we need to find the eigenvalues of the given matrix. Then we'd like to study how to find out the eigenvectors and the eigenvalues. So this is the equations for the A to satisfy when the x is the eigenvectors and the lambda is the eigenvalues. So from this equation, lambda x is moved to combine this equation. If the determinant of A minus lambda I is not 0, what happens? You can multiply inverse. In the both sides. Then this is a unit matrix. So this becomes x is 0. So this is a trivial solution. From these equations, inverse does not exist. So this means determinant of the A minus lambda I have to be equal to the 0. Then this becomes a polynomial equation. We could calculate the eigenvalues and substitute eigenvalue in the original equation that we obtained eigenvectors. So let's make some practice. In the case of the A equal 4 minus 2, 1, 1, then A minus lambda I is expressed 4 minus lambda minus 2, 1, 1 minus lambda. Once you get this a minus lambda I, you can calculate determinant a minus lambda I. So it becomes 4 minus lambda, 1 minus lambda, plus 2 equals 0. So by solving these equations, you can easily calculate lambda is 2 and 3. So this is the eigenvalues. So for each eigenvalues, lambda equal 2, you can calculate x equal lambda x. This is equals 2 minus 2, 1 minus 1, xy equals 0. So this means xy becomes 1, 1. If you substitute x equal 1, then y equal 1 is satisfied. We call it this is eigenvectors. And also for the case of the 4, lambda equals 3, x equal lambda x is expressed 1 minus 2, 1 minus 2, xy, 0. So eigenvectors is expressed 2, 1. Okay, so I explained how to discover the eigenvalues and also the corresponding eigenvectors. This is the end of this session.